Hello, my name is George C. Bradley, and today's presentation is on testing assumptions for multiple linear regression, or multiple regression using SPSS. Today's database will be HSB 500 dataset, and HSB stands for high school and beyond, and 500 is the cases that we have in this data set. The criterion variable is math achievement. Math achievement is a 25-item mathematical achievement test which scores range from negative 8.33 to 25. And we have three predicted variables, and the first one is visual. And visual is a 16-item test of visualization in 3 dimensions for determining how a 3-dimensional object would look. Number 2, mosaic. Mosaic is a 56-item test involving the detection of relationships in patterns of tiles, and the scores range from negative 28 to 56. And let me go back and give you the range for visual. It's negative 4 to 16. And our final variable is enrollment in Algebra 1. 1 indicates the student has taken the course, and 0 indicates that the student has not taken the course, and that's a dichotic variable, and 1 and 2 is continuous. And this data set is free and it's online. We have 2 main objectives here. The objectives, number 1, demonstrate how to test each assumption. And number 2, we want to talk about what to do if an assumption is not met. Assumptions for multiple linear regression. We have 6. There are others, but we'll talk about the 6 that we have here. Assumption 1 is sample size. Assumption 2 is outliers. Assumption 3 is multicollinearity. And assumption 4 is normality. And assumption 5 is linearity. And assumption 6 is homoscedasticity. And we will go over all 6 of these assumptions, not in this particular order. And sometimes we'll use 2, sometimes 3 different methods to test the assumption for 1 or more of these 6 assumptions. Let's take a look at our data set. And right here you can see we have our criterion, or our dependent variable, math achievement. And then we have our third predicted variable, Algebra 1. Our second, mosaic, and the first is visual. And you can see here that there we have 500 cases. Now we're going to look at we're going to look at assumption 4, normality, because that's the only one that we can check, not using the statistical test. So we can look at it with the statistical test, but I like looking at another method to find whether our dependent variable is normally distributed. We will go to analyze, and we'll go to descriptive statistics, We'll go right here. We'll go to Explore. We'll go to Explore, and then we'll click on Math Achievement. We'll put that in the dependent list. We'll go here to Statistic. We're okay here. We'll go here to Plot, and we will click out of Stem and Leaf and go to Histogram, and we'll click down at Normality Plot Test. Hit Continue. Options, nothing there. Display, we want to look at the statistics and the plot, and we will go and we'll take a look at our information. We'll go straight to Shapiro-Wilks. We have right here our degree of freedom, and our statistical significance is below 0.05. It's below 0.045. So that means our test for normality has been violated. But we have a very, very strong sample size here. It's way over 50, it's way over 100, it's 500, and that's strong. And normally with a sample size that size, with a case load that size, we're normally in a pretty good situation there. Now let's get back to our data set here. Our first assumption was sample size. Normally in multiple regression, we have 3 predicted variables, and for each variable you need about 20 cases, so that is met quite easily there. Let's go to Analyze. Let's go to Regression. Let's go to Linear, and let's put our dependent variable here. We only have 1, and we have 3 predictors: Visual, Mosaic, Algebra 1. We'll put that in there. We'll use the enter method. We'll go right here to Statistics, and we're going to click on Descriptive, Correlation, Linearity, and we're going to look at our Durbin-Watson. We'll put that in there. We only use our R-squared change when we're using hierarchical regression there. So we'll hit Continue. We go to our plot. Our plot here, this plot is very important because this visual representation that it will give you will solve almost 2 to 3, almost 4 different assumptions just by having this information. In our x-axis, we want to use the standardized predictors. Okay, and then in our y, we want to use our standardized residuals. We're going to look at our histogram and our normal probability. Once again, looking at some things with normality, I like to use the Shapiro-Wilks. Okay, we will hit Save. Now when we go up to Save, we want to look at a residual here. We want to look at our standardized residual there, and that's for an outlier. And then we're going to look at Cook's. If anything over 1 in Cook, we want to find that because that's a potential outlier. And with the standardized residuals, we have the range between -3 and +3. If you're on the left-hand side of the -3, we want to take a look at that. If you're on the right-hand side of a +3, we want to look at that potential outliers there. Let's hit Continuous. Continue. Nothing here with options. Don't have anything for bootstrapping. And now we're going to hit OK. Okay, we have our descriptive information here. And right here, we're going to look at correlation. And we're going to look at 2 things when we're looking at our multicollinearity. We're going to first, we're going to look at our predictors, and as we can see with our predictors, we want to make sure that we don't have any predictors correlating with each other that's above 0.8. And as you can see here, 0.28, 0.2, 0.1. So we're great in that area. And another thing you want to look at here, you want to see how your predicted variables correlate with your criterion variable, your dependent variable. And right here, the rule of thumb is you want to make sure that there is at least a 0.2 correlation. And as you can see, 0.4, 0.43, and 0.39, 0.29. And so everything is okay there and is significant. We move down here to our model summary. We can see since we violated the normality assumption, we'll look at the adjusted R squared, which is 0.331. That means what we have there, that the three predicted variables represent 33% of the variance for our criterion variable which is math achievement exam. Durbin-Watson, normally the Durbin-Watson range is from 0.5 to 2.5, so we're okay with that. Significant model here. All of our predictors are significant there. That's a good situation there. And we can see here with the VIF, nothing is over 10. So once again, something to validate our multicollinearity. Let's take a look now at our outliers. All right, over here with the standardized residual. Okay, we have a little problem here. This here too is to the left. It's to the left, and that means we might have a potential outlier. And right here, Cook's is okay. So we want to take a look at our data set. And let's take a look and see can we find at least one. It could be more than one, but this negative 4.261 is to the left of -3. So let's go to our data set. We can go to our data set, and this right here is the standard. We can click on there. We want to hit descending. Oh, there it is right there. And that is number 35. Well, let's take a look right there, 35. So normally when you have an outlier of that nature, one of the things that you can do with that, you can remove it. So let's remove it. We'll remove it. We'll bring this back. I'm sorry. Now we have a caseload of 499, and we remove case number 35. So let's go back. Let's go back here and let's run our multiple regression again. We have everything set up. We'll run it again. You can see a few things have changed here. You've gotten probably a better correlational look. Everything is about the same. All of our assumptions are met. But as you can see here now that we go to the standardized residual, that was met. That's met. And we have cooked. Now we are good with the outliers. We have our histogram here. Now let's take a look at our scattered chart with the regression standardized predicted variable in the actual x-axis and our standardized residual is in the y-axis. And let's take a picture. Let's look at this. Here is an example. Homoscedasticity. That's how it should look. It should be scattered. It should look random. Hetero, you can see like you're squeezing it in the middle. Hetero again looks here like it's a funnel. These are not good. The one to the left is good. So when we have that, we've just given you an example here of a picture. We've given you here a picture where you can see that we've met the assumption of homoscedasticity, and we have an example of, which I don't have here, but independent errors, and we have also where we can look at this, and it's with the assumption of linearity. Now we have other ways that we can test linearity, and I should have gone over that already, but let me go back and do that pretty quick. You put it in the proper order. Okay, and that's one of the reasons why I didn't use this particular graph, because you can't get a good pictorial look of whether it's linear or not. And that's not a good graph, but that's one of the ways that you look for linearity. And linearity is number 5 on our assumption list. So this is right here is the better picture that you can get right here. And it shows you that we met homoscedasticity and linearity with this particular picture. Let me try one more thing here. You can see how it's evenly divided there, and we can look at it. Let me go back here, and we can see how it's evenly divided in the opposite quadrants. Now, we're still in this graph here, and homoscedasticity, you can look at it on the visual component pictorially, or you can have an opportunity here. You can go and Google these two tests, and it can give you a statistical significance to actually see whether or not you have met or violated the assumption of homoscedasticity. So you have a pictorial component, and you also have something where you have a statistical test. Assumption 1, sample size. For each predicted variable, you need at least 20 cases. We had 499 because we have to take away 1, and we can get straight to that on assumption 2. With our standardized residual, it was to the left of -3, and case 35 was one that we deleted. So when we saw an outlier, we deleted it and we reanalyzed the data. You have that option. You can keep it there if you want to, but you have to see what makes sense when it comes to outliers. Multicollinearity, That was met. And if you have problems with multicollinearity, you can remove one of the predicted variables, or you can use ridge regression. You can use ridge regression. And be mindful that the point you need to keep in mind is when you're correlating the predicted variables, you want to make sure that they're not over 0.8 when you are correlating the predicted with the criteria, that it is at least above 0.2. And normality, that was violated there. And normally if it's violated and you have a huge sample size, you're okay, or you can transform the data. You can transform the data by logs, and you have other options there. Linearity, it was met. We saw the picture, but if it's not met, options transform the data or abandon the regression model. And homoscedasticity, there it was met, and you saw the options that you could use if you want to see a statistical difference. And keep in mind that if it's not met, you can transform the data, or you can use weighted least square regression. Weighted least squared regression. Are there any questions? If you have any questions pertaining to this presentation, please email GeorgeCBradley59@gmail.com.